this last part, I want to start with one topic that is actually quite crucial for collision detection, and that's convexity. Right, you might have noticed that all the shapes we have looked at so far, they're fairly simple, right? They don't contain any kinks or edges or curves or so. Turns out concave objects that have such kinks are actually a really bad idea for collision detection. Right, so concave object is defined as an object where if we pick 2 points within the volume and we draw a connection between them, we actually leave the object. Right? That means there is some dent or some region of the object that bends inwards, and this is actually really tricky for collision detection algorithms, because you can imagine, right, in this corner basically things can interlock, and the whole SAT, the separating axis test described before, that does not hold anymore. Right? We can have objects that don't collide. If I put something in here, they're actually not colliding, but I will not be able to find any viewpoint from which I can see that the objects are not colliding. So these we really want to avoid. What's nice for collision detection are convex objects, where these kinds of situations cannot arise. So all points within a convex object, if I draw a connection between them, will not leave the inner region. And that's also the reason why all the bounding volumes we looked at so far are actually convex shapes. They have inherent advantages for collision detection algorithms, and if you have concave ones, with nature of course, if I just look at my hand, a highly concave shape, we want to deal with such objects in a computer, then it's typically a good idea to actually break down the object into convex pieces. So for this L-shaped one, potentially you could break it down into one piece here and another one up there, and then we test for those. So there's a whole class of algorithms that actually decomposes concave objects into convex ones. They're known as some kind of convex decomposition algorithms, and then we can still use the algorithms I've described. So in general, these collision detection algorithms actually work with convex shapes. Yeah, so the kind of best convex shape for a certain object is typically denoted as a convex hull. You can imagine here that we basically take some arbitrary shape, we take a big rubber band or rubber foil, put it far outside the object, and then let it snap towards the actual geometry. And what we will get out then is the convex hull of that object. It's basically the smallest volume that is convex, but encloses the whole shape that we're given. Right, so this is mathematically also uniquely defined, right? The smallest convex set of points from which we can generate a surface to enclose the shape. And right here I have a small sample animation. If we have a collection of points, we can imagine snapping that with a rubber band from the outside, basically closing the sides of that object, the outer region. And right, we could also use this convex hull as a bounding volume primitive. There are actually some algorithms that do that. However, I don't want to go into detail here. As you can see a bit from this picture already, these convex hulls can be very complicated shapes. They're convex definitely, but they can have arbitrary polygons, they can have tiny pieces or very large flat areas. So in practice they are actually not so easy to work with. The shapes we've discussed so far are typically much easier to handle, and hence We will not go into details here, but just keep in mind the convex hull is actually, in a way, the best possible convex object for a given object. And being convex, the separating axis test still works here. So in a way, all we need to do for convex objects as well is to use suitable separating axis tests. The main challenge then is actually that we have these potentially more complicated geometries to deal with, arbitrary polygons. So there are two, just to name two examples, there are more, but there's a Voronoi-based algorithm. So Voronoi cells are defined as the closest point to the set of closest points to some chosen primitive or point, and these actually you can relate to convex objects and then also use them to perform collision detection. And another one is this so-called GJK algorithm that's also an optimized separating axis test for convex objects. So I think this GJK is actually, you can find it in the Bullet engine or other collision detection frameworks. If you're interested, you can actually look it up. But yeah, with that we've kind of covered the whole range here, and all these different possibilities to construct bounding volumes give us a nice trade-off. So on the right hand side here with the convex hull we have a better approximation. The convex hull really is also the volume-wise smallest shape to fully enclose an object we're interested in, but it's relatively complex. And on the other hand, we have shapes that in a way waste more empty volume, that are potentially too large, but very easy to deal with, and then typically also fast. So this in a way gives us the traditional trade-off, hardware resource versus speed of processing. Yeah. Now, with any of these, we have a primitive, a building block, from which we can now build a whole hierarchy to make it more flexible. So the following steps actually work for any of these. As I just mentioned before, for this S shape, even a convex hull is actually potentially not optimal. We could break that down. So even there you might be interested in actually building larger structures around it. And the main idea here is that we basically now make a whole tree structure, some form of tree structure, to give us more flexibility. So potentially the easiest way to look at this, if we take our S shape that was on the slides many times now, the easiest way is a kind of top-down procedure where, in this case, we would take an oriented bounding box, fit it to our shape, and then to prove the approximation, we would break this down, for example, along the longest axis that we had. Then in the next level, we would basically split the geometry, So here we had a split of the bounding volume, and now that gives us one region of triangles and then this upper part here. These are now basically two new objects that we're trying to fit, and here we're actually doing that with one bounding box and with another one. And then we can continue. Same game, we can split the object here, get two pieces, and then here another two for this and this one. And as you can see here in the last stage, we're actually approximating this S shape quite well. As I hope you can also see, when we're doing this, there's actually no guarantee that objects will not end up in multiple of these bounding volumes. So in this case, if you look at the triangle here in the corner, this is actually belonging to both this bounding box and to the next one. It's intersecting both, so this triangle will actually show up 2 times in each of our bounding volumes, especially in these connection parts. That's often inevitable, and due to this, actually the number of primitives potentially increases because we have duplicates. In general, for most practical case, we cannot guarantee that we really clearly can separate the parts of an object. And again, that's not bad, but it might increase the workload downstream for narrow phase tests. Yeah, so here we can, or let me outline a few different strategies how we can go. What we just described was a top-down approach. You can also go the other way. You can basically go from the primitive level upwards. Then we take a whole collection of primitives. In the simplest case, really fit a bounding volume to each of them. It's typically a good starting point for next steps, or directly start with them and then recursively group them. For example, by finding some characteristic distance, some if it's a pre-computation, we might be able to spend more time, or some rough estimates of how they are arranged. And then we basically fit a new bounding volume, whatever it is we're using, oriented bounding boxes, so around this group. And then we start grouping the groups until we're just left with basically one big bounding volume for everything. Top-down is the other variant that I just illustrated with this S. Start with one big one and then subdivide. Right. Actually, that I can, while I have a slide here, I can quickly draw. If we imagine we have some setup of few triangles that are now just spread out around the plane. Let's call them A, B, C, and D. And I just showed the top-down structure where we start with the big one and subdivide. So let me illustrate the other way around, the bottom-up. Right, we have to find some approximate distance. Let's maybe start connecting these two pairs here with an axis-line bounding box. So this might be a first, let's just number it, a first bounding box here. So this would then, in our hierarchy, in our tree, this would be a first leaf node. Then we're left with objects A and B. So let's fit another box around these. And this would now be a second one. Getting another leaf node here, and both of these leaves now contain some of our primitives. So in this case, we actually, this works nicely. They're separated, none of them is duplicate. If they're overlapping, we could have some of them more than once. And then we would go in and now treat these two bounding boxes as one object. And in this case, it's pretty simple. We would basically put one more layer around both of them. In this case, the 3, which would be the root of the tree. So we'd have a hierarchy as the one shown here. So this would now be a bottom-up strategy in contrast to the one I just showed for the S shape. Yeah. Another variant is what's called insertion, insertion-based hierarchy. So here, this is a bit primitive if you want. We're just taking a stream of primitives or bounding volumes as they come and insert them into the tree. So in this case, we basically have a partial tree. We're getting a new object, we're putting it into the tree, and then if there are too many objects, basically create a joint node and potentially split that node if too many objects end up in this part of the tree. So in a way, it's fairly simple. An advantage here is that we could potentially do dynamic updates here. We can remove objects and then also add new ones, or add the same object with a new position. So it gives us quite some flexibility. Disadvantage is that, as in all of these cases, we depend on the order and we get a kind of deteriorated worst case ordering. Then we end up with a structure that looks more like a list than a tree, and then the whole logarithmic advantage of the branching gets lost and the tree would be slow. But yeah, we gain the flexibility. All right. It's also worth mentioning that there's a whole range of parameters for these construction strategies. Right? So first we have to choose the type of bounding volume, which way to go, top down, bottom up, or also for these we actually can then have different subdivision strategies. We take the midpoint of the current bounding volume to try to find a median. We could try to optimize, basically invest resources to find a good split. We have parameters like how many of the primitives would be allowed in one of the leaves of a tree. Optionally, it's also possible to resample the object, so we could even change the geometry when inserting to better fit to the tree. So there are lots of ways to do this. The main goal is we'd ideally like to have a balanced tree, right? The shallower the tree is, the more we get out of it in terms of complexity necessary to traverse the tree. We also want minimal volume to make it efficient, and also to avoid that the bounding volumes we insert and store overlap many of the objects. Then we get this duplication that I've mentioned before, potentially again lowering the efficiency of the hierarchy we generated. So yeah, I have a nice picture here of a cube soup. So this is just a messy accumulation of cube shapes, right? And this would be the nightmare for any collision data structure, because they just intersect everywhere, right? There's no way we can do well here and separate them. This actually violates this far away assumption, right? Right, if you imagine this being a bounding volume hierarchy, it's still bad. It actually wastes a lot of space. So the takeaway here a bit is that these hierarchies have parameters and are quite problem dependent. So to really work well with them, we need to adapt it, adapt whatever the algorithm is we're using to the application at hand to get a good performance out of them. Assuming we have a nice hierarchy now, we somehow subdivided our object or scene successfully, then we're usually relatively well off. If we have a balanced tree structure, then it's very efficient to check for collisions. So here is a simple example with these S-shapes. So 1 and 2, and you can directly see visually that they're intersecting here. But if we're just given all of these triangles, that actually would be a bit tricky to find out. Now what we want to avoid, obviously, is just having to intersect every triangle with every other one. So if we have a bounding sphere-based hierarchy, as shown here, what we can now do is we can start at the root of each of the hierarchies and check whether the primitives, in this case the bounding spheres, intersect. Well, they do. They have to, because they enclose our shapes. By definition, a bounding volume has to have a larger volume, so the shapes intersect, hence the bounding volumes have to intersect as well. Now we can drill down into the hierarchy, go to the next level, and now we just need to check the primitives at that level. So pretty clear. Now we're given smaller bounding spheres, and we will find this pair that is still intersecting and continue going down and checking the resulting lower level spheres here, and then assuming that this is actually our leaves in the hierarchies, then we're left with these triangles. And now for these we really have to go to the narrow phase and test all the triangles against each other to actually find this pair that intersects. But for the traversal now, we had something that's actually logarithmic in the number of primitives, and these checks for the spheres can be done very, very efficiently. So this whole procedure, once we're done with the pre-computation, is actually very efficient to compute. Yeah, so now I want to get back to this far away assumption. So one of the worst cases really for collision detection that can happen is what's often called a parallel close proximity case. So here the challenge is that if we have shapes that not only are not far away, but are very similar or share a lot of geometry and are somewhat aligned. Again, visually we can see very clearly that these two kind of curved L's, they are not intersecting, but this is actually really tough for collision detection algorithms to find out. I hope you can imagine by now, if we try to fit this with bounding spheres, the spheres will naturally give us some orthogonal extent. And in this case, they would overlap all over ABBs or K-dots. In this case, also would have trouble. They would potentially still be intersecting here. And in this example, actually with OBBs, we would just barely, so I hope you can see it here, just barely separate these objects. But yeah, also for the hierarchies, what's crucial is basically that we can successfully separate with the bounding volumes the objects at the lower levels. So in these cases, in all of these, potentially the higher level primitives would overlap. Luckily for the hierarchies, these are basically orders fewer. And what should be avoided, if somehow possible, is that at the lower levels we actually have these overlapping bounding volumes. Those would really cause work for the narrow phase. Yeah, I have another nice example here. Here now we have a torus shape, and we're approximating this with a hierarchy of or kind of side-by-side hierarchy of AABBs and OBBs, and here this nicely shows the different approximative capabilities of these building blocks. So yeah, for an AABB in the first phase, actually we cannot really make out this donut shape at all. It would close up in the middle. OBB would already roughly recover it. In the next level, we also at least have this opening here in the AABB, and then you can see as we progress more and more, especially this curve shape, this is actually quite well approximated by the OBB, so these levels here don't change too much, whereas with the AABBs, yeah, even at this 7th level, which already contains quite a number of nodes in the hierarchy, you can still have some pretty jagged edges. And here at level 9, finally we're starting to really see the torus shape that we're interested in. I don't have the exact numbers of how many primitives are used in each cases, but you can roughly guess from the level here how many there are. Yeah, some closing remarks on these data structures. I've mentioned it briefly before, but these different the different bounding volumes do behave differently when our objects are changing. Right, so the bounding spheres actually can handle translation and rotation naturally, because they're radially symmetric. I can rotate in here in any way. If this viewer is fit to the center, I don't need to change anything. Both the AABBs and KDOPs actually don't support rotation. So if my object is rotating, I would need to recompute. This is an advantage of the bounding boxes, and also the convex hulls actually would attach to the object and move along with it. Depending on the situation, these properties can be a plus and offset some of the cost for OBBs or potentially even convex hulls. Yeah, then I might also have objects that actually deform, right? Think of our mass spring systems. If I want to do a fast collision detection with mass spring systems, they're deforming all the time. It doesn't make much sense to pre-compute something complex, because as soon as I start the simulation, the configuration and the vertices will change a lot. So one way to deal with this, actually, we will look at this a bit more later on with a more refined algorithm. But we can actually do this to some extent already with such a hierarchy. So what you could do here is, especially if only parts of the geometry change. If the whole object changes, then it's probably best to recompute. But if, say from a collision, only a part of my object changes a lot, I can actually go into the corresponding leaf nodes, update the vertices there, and then basically from that changed leaf go all the way upwards into the tree towards the root and update the primitives. I hope you can imagine. Again, there are too many different variants to do this. I don't want to go into all the detail here, but you can imagine that there are efficient strategies, or at least some strategies, to update the hierarchies here to also accommodate for deforming and changing objects. Yeah, especially if I don't do any additional splitting or so, then I would potentially get shapes that are suboptimal, that spheres that are too big or so. So I might have to do some reordering, some heuristics to split shapes, so that I get back to reasonably shaped bounding volumes again. But as mentioned before, actually, we will have a more dedicated algorithm for deforming objects coming up later that works quite neatly. So this is more of an outlook. All right, yeah, with that I'm already at the end of today's lecture. So I described these culling algorithms as different variants of broad phase approaches, the vision-based ones, the skull light algorithm and the sweep and prune, and then the different bounding volumes and some strategies how to construct hierarchies from them. This is actually a pretty widely used and a generic approach. And next week we'll then look at different spatial partitioning structures. So the main difference here is that so far we took a very object-centered view. We basically had our objects and then tried to fit bounding volumes or split them up based on the objects themselves. And in the next lecture we'll take a bit more the viewpoint that we're just looking at the space between the object, the whole region, and then we'll try to construct data structures that partition, organize the space so that we can then store the objects in these spatial regions and later on drill down to the objects and perform collision detection there. So you can imagine this also will give us tree-like structures later on. Yeah. Oh yeah, and then also we look at sign distance function as a interesting representation for objects that's especially suitable for collision detections. All right, and with that, see you next week.